Welcome back, everybody. So this is the second day out of section 5.2. I didn't say Kyla was out. Hold on. Hold, please. Hold, please.
Have you seen the famous big feta recipe now? That's so gross.
No.
Is it gross?
I'm not a fan of feta.
Why?
I don't know.
Not a fan of
All right. So we're talking about definite integrals. Definite integrals. Now, what is it? What is an integral? An integral and performing integration is basically just finding the area underneath a curve, right? Finding the area underneath a curve. That's really what integration. I'm sorry. That's
okay.
It's really finding the area underneath the curve. That's what the process of integration is. Now, what we're going to do today, I'm going to introduce how antiderivatives tie in with integration. Okay? We're going to tie in antiderivatives with integration. We learned about this special new symbol here, this integration symbol. Let me go to where the summary is. Yeah, right here. We learned we talked a lot about where integration comes from, what the background of it is, what all the different pieces and parts yesterday. Mr. Ivan, here to take his test. Hold on one second, folks.
Good luck, Ivan.
Good to see you, friend. Thank you for coming. Here.
Mr. Brand. What you doing?
Here you go, sir. Head out in the hallway. You got your calculator with you? Yeah. Perfect. You got your lunch with you? Yeah. Perfect. All right. So we say that to perform the integral, you need an upper boundary and a lower boundary, right? Especially for a definite integral. You need an upper boundary and a lower boundary, and you're going to say along a function, find the area underneath that curve. And we were drawing this diagram yesterday. I think I drew it on the whiteboard here. Where you can have some function, say we're going, I don't know, and we've got here's A and here's B. The integral is really equal to the area from here to here underneath that curve. That's what really that is equal to. Okay? From A to B of fx dx. That's the integral. Remember that shape, that symbol is just like a stretched out S, referencing sum, referencing the sum of all the rectangles within there. Okay, that's what we're really looking at there. And it could have some discontinuities in there. It could have a jump discontinuity. That's fine. That doesn't affect the area. We talked about that. But yeah, so this is really very similar to what we were doing in section 5.1. Just finding the area underneath the curve. We just transferred from summation notation to integration notation. And now we were here, right? We talked about the Riemann sum. The Riemann sum is just basically that sum, the value of that sum, right? The sum of f of si times delta x. All of the areas added together. Okay, of a definite integral. Okay, going from 1 to 6, we calculated 6 strips of rectangles. Taking the sum of all of those 6 strips of rectangles, we found that the Riemann sum would be negative 3.9375. Now, what we're going to take a look at next is we're going to evaluate from 0 to 3. We're going to evaluate this piece here, okay? And I'm going to show you 2 different ways to evaluate it. The first way is the much more difficult way. And the second way, I really shouldn't introduce to you until section 5.3, but I'm going to cheat. That's not what I'm saying. I'm saying that I don't know if I would make you do this first part on a clear test. Yeah, it's just a kind of a difficult process. I'm going to bring it to a new page real quick.
I think you should start using more fun colors.
Well, my color's not fun right now?
Well, there's more options.
I know there's more options, but, I mean, there?
Yeah.
Okay, that's okay. Okay, how's that? That's good, okay. Is that all right?
Yeah.
All right, see, but now if I go switch off it back onto it, it's gonna be gone.
Yeah,
I'm just using it. All right, so now let's first start off by figuring out, by going from the integration notation to the summation notation. Let's first figure out going from the integration notation to the summation notation. So that means that I want to go from 0 to 3 of x to the third minus 6x dx. Remember, what is this referencing? This is referencing, you're going to have to take the function and plug things into the function and multiply it by some delta x. Hold on a sec, we need to wait for Mr. Hudson to come in. Everybody clap when he comes in. Ah, he's not gonna come in. Did you need something? He's so weird. All right, so this is really like saying the sum going from, oh, I forgot my limit symbol. The limits as n goes to infinity of the sum of from 1 to n of f of xi oh, I shouldn't say dx, I should say delta x, sorry. Delta x. Where I know that delta x is what? Well, what are my endpoints? 3 and 0. So I could take 3 minus 0 over n. So delta x is 3 over n. Right? Well, that means that my xi is my original value, 0, plus delta xi. Right? That's the formula, delta xi. So 3 over n times I. I'm going to write it as 3i over n. So here's what we have here. We have the limit as n goes to infinity, going from 1 to n of f of 3i over n times 3 over n. Please try to understand what's happening with the notation. This notation is saying that I'm going to find all the different sums of the difference on x, the base of each rectangle, times the height of each rectangle. That is 3i over n, plugging it into the function. That's the y value. Because I'm going to plug in 3 times 1 over n. I'm going to plug in 3 times 2 over n, plug in 3 times 3 over n, plug in 3 times 4 over n, and keep on going until I equals n. 3n over n. Right? That's really what we're doing there. So let's write. Let's actually plug that in. When I say plug that in, I mean plug it into the equation because we know what the equation is. Right? So that is the limit as n goes to infinity of the sum from I going to 1 to n. And now let's plug in 3i over n. So this is going to be 3i over n cubed minus 6 times 3i over n, all times 3 over n. And you know what I'm going to do? I'm going to sneak that 3 over n. I'm going to sneak that out. I'm going to sneak that on the outside. Why can I do that? Because it's multiplying all of those pieces, and guess what? That's like the GCF. Remember doing that? Like that's how I was showing all of my sums. Multiplying the delta x times all of my y values added together. Because I would just be distributing that time anyway. Yes.
I might have zoned out. Where did you get the 3i over n from?
The 3i over n came from xi. And remember, the formula for xi was a plus delta x times I. The formula for, you know what I'm saying? I'm going right here. A plus I times delta x. And since delta x is 3 over n, it's I times 3 over n, or in other words, 3I over n. Okay, so let's just start reducing down and see what happens. Okay. So that's equal to the limit as n goes to infinity of 3 over n times the sum of, from I going to 1 to n, 27 I to the third over n to the third minus 18I over n. You all follow me there? All I did was just distribute with the third power and multiply in the 6. I did. It's sitting out front. Yeah. There's a lot of 3 over, there's a lot of 3 over n's because that was the, that's the delta x, and that's a piece of what goes into the function as well. So you're seeing it not only as the x value that's being multiplied to all the y values, but you're also seeing it plugged in as the x value to generate the y value.
You don't actually take that out.
Right, all I'm doing is just removing, this is just delta x sitting on the outside. Yeah, just like our half-second intervals, things like that, that's sitting on the outside. That 0.5 sitting on the outside.
Why does it matter if it's over there? It doesn't really do anything?
It matters because that n, I'm gonna have to make that go to infinity in the end. So I'm gonna need to evaluate what this sum is gonna be. I'm gonna keep plugging away here and then multiply it in the end and see what my limit will go to. Let's keep moving here. Excuse me. Where am I at here? Where am I at? Okay. Lost my place now. 6 here. 21. Nope, you're fine. Okay, I'm here. And I'm going to 81 over n to the 4th. Oh, got it. Now, watch what's going to happen. I guess I didn't really need to bring that up front because I'm going to bring that in now. So sorry, I kind of confused you. If that. Right. What I'm going to do now, because that can come out back and forth because it's not dependent upon I, right? So I'm going to distribute this in now. I'm going to multiply that in. And now that's going to get me the limit as n goes to infinity of, from I equals 1 to n, 81 I to the third over n to the 4th minus, what's that, 54? Yeah, 54 over n squared. 54I over n squared. Okay. Now, I'm going to do some properties of sums real quick. We learned yesterday that the sum, if I have a summation on a difference, I can take those two pieces and find the sum of them. So I'm just going to basically distribute this sum notation to both parts. So that's really going to equal to the limit as n goes to infinity of the sum as I goes to 1 to n of 81 I to the third over n to the 4th minus the sum of I going to 1 to n of 54 I over n squared Now, try to remember that the only thing that's changing in the summation notation is I, right? I is the thing that keeps getting increased and increased and increased, right? It's not n, but I. So honestly, isn't n just a constant, really? It's not being changed by the summation notation. I is what's being changed. I is going from 1 to 2 to 3 to 4, 5 to 6, all the way up to n. And it's just the end point. It's not really like a variable in there. So what I'm going to do is I'm going to pull it out like a constant. So it's the limit as n goes to infinity of 81 over n to the fourth times the sum of I going to 1 to n of just I to the third. Minus, and I'm going to do the same thing. I'm going to bring the 54 n over n squared out. And that's going to leave me with just the sum going from I to 1 to n of just I.
You don't have to rewrite the limit.
It's there. It's just over here.
So
I mean, I guess I could write it like that. You know what I mean? Now, how does that help us? How does that help us? Well, I'm going to use, remember I said I was going to use it yesterday. I'm going to use this piece, and I'm going to use this. I'm going to use those two things. It's funny. What did they say? They say something kind of funny in this upper paragraph. I was reading those, but that's weird. The following three equations give formulas for sums of powers of positive integers. Equation 5 may be familiar to you from a course in algebra. Like, oh, really? Like, you really know that from some algebra course? Right, like you guys know that formula, like, right, like I going, this is n times n plus 1 over 2, right? See, these three formulas are used a lot when proving these limits. Right? That's why I'm really not going to test you on this kind of stuff. I'm gonna test you more on the other stuff, but I want to show you. I want you to appreciate the easy side of this because I need you to see where it comes from. No. This is not the easy side. This is not. Don't worry about that. Yeah, no. Don't worry about that. So let's keep it going here. So we saw from the other page that this is going to equal to the limit as n goes to infinity of 81 over n to the fourth times, now I to the third is n times n plus 1 over 2 all squared minus 54 over n squared times n plus 1 all over 2. All I did was replace this in here with this, and this right here with this. Because what's gone now is the summation notation. What's gone is the summation notation. And now, once I evaluate this down, once I reduce this down, I'm going to be able to evaluate the limit. Yeah.
You might have said this, but why did you square the one parenthesis and not the other?
That was just the formula.
Okay.
That was just I to the third formula.
Got it.
Okay, so let's try to reduce down this expression and to see if we can evaluate this limit. Because look, I've got the limit as n goes to infinity. So if I can make some sort of fraction things, if I can see what's going on with some fractions, I might be able to send the denominators equal to 0, send the denominators to infinity, and make those all go to 0 and figure out what I can evaluate this limit to actually be. So let's reduce down this expression. I'm just gonna take a little sidestep and just reduce down these expressions. So let's go here. This is just the yellow. That n times n plus 1 over 2 squared. So that's n times n plus 1 over 2 squared is going to be equal to n squared plus n over 2 squared which is, okay, that's n squared plus n squared over 4, which turns out to be, okay, I've got a FOIL n squared plus n to the 4th. Outer is n to the 3rd, inner is n to the 3rd plus 2 n to the 3rd, and then n times n would be n squared. All I did was just reduce down that expression, n times n plus 1 all over 4 squared, or sorry, all over 2 squared. Let's do the purple. Let's reduce down the purple. So all that is, I just got to distribute that. Let me write out the original. N times n plus 1 all over. What do you do? See, my smart board's freaking out. It's like, what? You're doing way too much. So n squared plus n over 2. Oh, that was easy. That was a lot easier simplification. So now, what that means is I've got the limit as n gets bigger and bigger of 81 over n to the 4th times this yellow piece, n to the 4th plus 2n cubed plus n squared all over 4, minus 54 over n squared times n squared plus n all over 2. Okay, let's bring it in. Let's bring in these pieces here. So the limit as n goes to infinity of 81 n to the 4th plus 162 n to the 3rd plus 81 n squared, all divided by 4n to the 4th. Just multiplied my two fractions together. Minus 54 n squared plus 54n all over 2n squared. And now I'm going to uncommon the denominator. Yep, of course. That's okay. I'm not gonna let that go above the page.
Okay, good.
I'm gonna make this denominator go to each piece and make this denominator go to each piece and see what happens here. This is gonna be 81 n to the 4th over 4n to the 4th. Well, my n to the 4ths are gonna cancel, leaving me just an 81 over 4, right? I'm gonna do the same thing here, but this is gonna get me 162 divided by 4. That should be 81 over 2. And then an n sitting left over on the bottom, right? This is going to be 81 over 4. And n squared over n to the 4th is going to be n squared sitting in the bottom. All I'm doing here is taking the denominator to each piece of the numerator. Minus 54, do the same thing. That can reduce. Yeah, I just reduced it to 81 over 2. Okay. But 6 of one, half dozen of the other, you know. I've got 54 over 2, which is just end up being 27, right? And n squared over n squared is going to cancel here, and then do it to here, plus, and that's a big plus there, or a big parenthesis there. 24 over 2, that's 27 over n. Now, that's the limit of all of that. What's going to happen when I evaluate that limit? Yeah, that gonna go to 0. This gonna go to 0. This gonna go to 0. Right? So the only things left over, and these are just constants, right? Those are just numbers. So that stays. So 81 over 4 minus 27. Okay. 81 over 4 minus 27. Negative 6.75. Whoa. That's the area underneath that curve. Can I show you something?
Yeah.
See, your book says you're only supposed to do section 5.2 like that. You're supposed to stay like that. Well, let me show you a little shortcut here. Okay? Because that's what the integral equals. Right? That's what the integral equals. Let me copy and paste this. Copy. New page. Edit paste. Okay. Okay. Now, another way to write an integral from a to b of f of x dx is capital F of x, vertical line a, b. So what is capital F? The antiderivative. The antiderivative. What's this vertical line business then? That vertical line is a notation that says f of b minus f of a. So you mean to tell me that if I find the antiderivative, and then I plug in 3, and then I plug in 0, that the difference of that gets me all the way to the end of the other problem? What's the antiderivative here? X to the 4th over 4 minus 6x squared over 2 plus a constant, right? You don't worry about the constant. Okay, so that's really going to equal x to the 4th over 4 minus 3x squared from b to a. And b is 3, and a is 0. Okay, so let's plug in 3. 3 to the 4th is 81 over 4. What? Minus 3 times 9, which is 27. What? What do I get when I plug in 0 to all of this stuff? Right? I just get 0 when I plug this all in. 0 to the 4th is 0 over 4 is 0. Minus 3 times 0 squared, which is 0. So I get a bit minus 0. So you mean it's what? What? 81 fourth over 27, or minus 27 is negative 6.75.
No, do you not have to have the constant?
Kind of. Yeah, the constant doesn't matter anymore because all the constant was doing was vertically shifting it up and down, which has no effect on the full area left and right. That's really why. Okay. So we will learn this in section 7.3 a little bit more in depth. Okay? 5.3, sorry, 5.3. 5.3. And we will learn this in section 5.3 just a little bit more in depth. Just a little bit. I don't know, there may be like just 1 or 2 problems on the homework that you can use that on. The rest of them are really just finding areas underneath curves, sketching it based on area underneath, like what does it look like the area is, gives you a graph, find the area and whatnot. But let me see, what time is it? 10:45, I've got 15 minutes, right? Let's do one more example so we don't have to do it on the video. Yeah. I'm gonna have to give you a video over a couple problems on Monday. Let's do example 4, then we'll stop here at example 4. Evaluate the following integrals by interpreting each in terms of area. Now, could I possibly do the antiderivative for the first one? It's not just a polynomial, so no. It's not just a polynomial, so no, I cannot. See, there are some that you can find the antiderivative of, and some that you cannot. Right? Like this first one here, I cannot find the antiderivative of. So I'm going to approximate it using area. What does that mean? That means I need to go to the graph, and I need to figure out based on the graph, what is the area of this thing? Okay, so now what's the function then? F of x is equal to the square root of 1 minus x squared. Now what does that look like? Well, isn't f of x just y? So if I square the opposite side, I'm going to get y squared is equal to 1 minus x squared. Let's bring it over. What is that? What is that? A circle. It's a circle. And since I only have the positive root here, it's only the top half of the circle. Right? It's only the top half of the circle because I only have the positive root given to me. So I'm going to graph it. What's the radius of that circle? 1 unit. That's a pretty good, it's a little bit off center, but it's a pretty good circle right here. Now, what is the integral symbol telling me I want to only find the area of? From 0 to 1. From the x value of 0 to the x value of 1. So basically just that. Radius 1, bless you. So that means the area is equal to 1/4 of the area of the circle, pi times 1 squared. Or in other words, area is equal to pi over 4. So that's equal to pi over 4. The integral from 0 to 1 of the square root of 1 minus x squared dx is pi over 4. See how it's just a number? Remember I was trying to reinforce that yesterday where the integral is just equal to a number. It's just equal to the area, right? It's not equal to another equation. We might use the antiderivative, we might use another equation to get there, but now, could we possibly use that whole antiderivative thing here for this next one?
Yeah.
Yes, but I want to show you in terms of area, and then I'll go back and show you the antiderivative. Because the area is actually pretty easy to find. Isn't this function just x minus 1? Okay, y-intercept negative 1, slope of 1. Let's graph it. Right? Y-intercept of negative 1, slope of 1. Up 1 over 1, up 1. I got to go to 3. So if I plug in 3, I get 2, right? I use blue. I plug in 1, I get 0. Plug in 2. Ooh, shouldn't curve. Should not curve. Should be a straight line there. There we go. Okay. I want to find the area here. Now, remember, underneath the x-axis should be interpreted as a negative area, right? So I'm just going to find these two separate areas. Let's find the red area, and then we'll find the green area. Area 1, area 2, whatever you want to use for as a notation. The area, let's call it area 1. Let's call it area 51. Let's call it area 1. Well, area 1 is a little triangle, 1/2 base times height. And again, we interpret it as negative. So area 1 is negative 1/2. Area 2 is, okay, area 2 is positive 1/2 base times height. Okay, so 2 times 2 is 4, 1/2 of that is 2. So my total area, this is equal to 2 minus 1/2. So 1.5. In terms of the antiderivative, Like how would that look using the section 5.3 thing that we'll do? Well, remember that's big F of X from B to A. We put the upper bound on the top, I believe. Yeah, top minus bottom. It's always top minus bottom. Yep. B to A. So that would be equal to, all right, X squared over 2 minus 1X from 3 to 0. The nice thing again here, when you start at 0, life's really good because you're not gonna have anything to subtract. So we say that's going to be equal to 3 squared over 2 minus 3, and then a big minus 0. So 9 over 2, which is 4.5, minus 3 minus 0 is 1.5. You see how that works? Okay. In the homeworks, I ask you to do a lot of area given a graph and area using the graph. If you want to confirm that using the whole antiderivative thing, I try to push you to do more like areas using graph of the function, like these two, okay? Because we'll get to a point where we'll just be doing this all the time. All right, we'll stop there and I'll start up with the midpoint rule on the video.